Today we will look at energy. Again, you may have seen some of these concepts in the past, but energy provides the basis of all thermodynamics analysis, so it may be good to start from the beginning. Energy exists in many forms: mechanical, heat, kinetic, chemical, etc. The first four, the ones listed here, are the ones we will see most in this class. If we take the sum of all of these forms of energy together, we get the total energy of some object. This is denoted by capital E. We also often deal with the energy per unit mass, or a specific energy, denoted little e. The actual value of energy is actually irrelevant, as the 0 point can be assigned arbitrarily. Therefore, we usually deal with changes in energy. That is the important quantity in thermodynamics. Energy can be split into many categories. We saw one classification on the previous slide that dealt with many types of energy. Energy can be split into many categories. We saw one classification on the previous slide that dealt with types of energy. It can also be based on scale. There are macroscopic and microscopic forms of energy. Macroscopic forms are things we can see, such as motion, kinetic energy, as well as things like gravitational potential energy and electrical energy. The kinetic energy is given by Ke and can be calculated through 1/2 mv squared. Note that little v here is velocity. We also have the specific kinetic energy given by lowercase ke and without the contribution of mass. This is for an object that is going through translational motion. There's also a form of kinetic energy associated with rotational motion. In this case, Ke equals 1/2 I omega squared, where I is the mass moment of inertia and omega is the angular velocity in radians per second. If an object is both translating and rotating, the total kinetic energy would be the sum of these two contributions. The other common form of macroscopic energy is potential energy. This also comes in many forms of its own. Two of the most popular are gravitational, Pe sub g, which is equal to mgz, where z is a vertical coordinate measured from some arbitrary 0 point and up being positive. There is, of course, also a per unit mass version of this, as seen here. The second common type of potential energy is spring potential energy. This is the energy stored in a spring that has been either compressed or extended. It is given by Pe sub s and is equal to 1/2 kx minus x0 squared. Here k is the spring constant and x0 is the relaxed length of the spring when it's not compressed or extended. Other forms of macroscopic energy, electric, etc., can also be treated as potential energies. However, these are not that common in thermodynamics, and we can usually assume that these are not relevant to the problem unless otherwise noted. Microscopic energy is related to the molecular structure and movement of the individual molecules that make up the macroscopic object. These include such things as the kinetic and vibrational energy of the individual particles, as well as any spin energies, and also any energy associated with binding forces. The total of all these microscopic contributions to the energy is called the internal energy, capital U. The average velocity of the individual particles is related to the temperature of the object. The total energy of a system is then the sum of all the macroscopic and microscopic forms of energy, so E equals U plus Ke plus Pe, or the per unit mass version of this seen here. A stationary system is a closed system that does not move. If a system is stationary, then there is no kinetic or change in potential energy. In this case, the only change in total energy can come from a change in internal energy of the system, or delta E equals delta U. The forms of energy discussed so far are called static forms of energy. They are contained within the system and do not leave the system. Dynamic forms of energy are those which do enter or leave the system. These are the ways that energy can be transferred between objects. In a closed system, there are two types of dynamic energy: heat and work. Heat transfer occurs if there is a temperature difference between the system and the surroundings. Work energy transfer generally comes from the interaction of forces between the two objects. Remember that work is equal to force times displacement. Mechanical energy is comprised of kinetic and potential energies, as well as any flow energy contained in the fluid. This is most commonly related to the pressure. It does not contain any thermal or chemical energies. It could, though, contain other forms of energy associated with work, such as friction. Since there is no heat transfer involved, the system will remain at a constant temperature. The mechanical energy is then given by E equals P, pressure, over rho, density, plus V squared over 2, plus GZ. Note that this is per unit mass. You can also have the regular version by just adding mass into all of these terms. In addition to this, we also often use rates of energy transfer. This is how the energy is changing per unit time, so E divided by T. This is also equal to the specific energy, little e, times the mass flow rate, m dot, which is equal to mass over time. Note that rates are usually denoted by dots, as seen here. Two objects at different temperatures will exchange heat until they get to the same temperature, assuming this heat transfer is possible. In other words, the objects are not insulated, but are actually in thermal contact. This is known as thermal equilibrium. So temperature difference is the driving force behind heat transfer. Without a temperature difference, there is no heat transfer involved. Any process that does not involve heat transfer is called adiabatic. A system can be adiabatic by either being at the same temperature as the surroundings or by being thermally insulated from its environment. Note that just because a process is isothermal does not mean it is adiabatic. There could be equal amounts of work and heat coming in and out, keeping the temperature constant. Heat transfer is denoted by Q and also has the per unit mass form, little q, as well as heat transfer rates per unit time, denoted by dots over the q's. There are three processes in which heat can be transferred: conduction, convection, and radiation. The details of those are not going to be important for this class. In fact, that is a whole other class in and of itself. Here, all we care about is the amount of heat being transferred. We don't care too much about the how. Work is another mechanism to transfer energy between two objects. Work basically is any type of energy transfer that is not heat. It is usually due to a force interaction between two objects that causes some displacement. Work is denoted by W, and just like heat has both specific forms, little w per unit mass, as well as rate forms, W dot per unit time. There is a big difference between energy coming into the system and energy going out. Therefore, both heat and work are directional quantities. However, this direction can be completely defined by a sign convention, plus or minus. Now, unfortunately, the standard thermodynamics sign conventions are not entirely intuitive. Heat transferred to a system and work done by the system are both positive, while heat transferred from a system and work done on a system are negative. Note that this means that heat added to a system is positive, but energy leaving the system due to work is also positive. Similarly, work energy coming into the system is actually negative. Keep this in mind when you are performing your analysis. Another common way to do things, and is the way I prefer, is to have subscripts on work, so W in and W out. I find this easier as a proper sign can be attributed to each, negative for W out, positive for W in. The key is to be consistent with the overall energy of the system. We will talk a lot more about this in the next video. A few things to keep in mind when dealing with heat and work. They both only act at the boundary of a system, not inside it. Because of this, the system does not contain heat or work like it does with other forms of energy. Similarly, these other forms of energy help to define the state of the system. Heat and work are associated with processes, not with the state of the system. They help to define how the system is changing. Both heat and work depend not only on the initial and final states of the system, but also how it goes between the two. The state of the system depends only on the relevant variables at a certain point. On the other hand, path functions depend on how this change actually occurs. For example, we can have a change in volume, delta V. Regardless of how this came about, the change in volume is the same. However, the amount of work depends on the process path in which this change of volume occurred. This can be seen here with these two processes, A and B. Same change in volume, but different amounts of work required. For this reason, point functions are generally written with exact differentials, d. Upon integration, they simply give the difference, v2 minus v1 in this case, whereas path functions have inexact differentials, delta. These integrals depend on the path, and so can give different values for the same endpoints. There are many types of work that can be done on a system. One of the more popular ones is from electrical power. Note that power is energy over time, so power is actually equal to the rate of work being done, or capital W dot. Electrical power is then given by voltage times current, or W dot equals V times I, where I is current, and voltage has been given the symbol phi here, mainly because we already have way too many V's in this class. You may be more familiar with this equation in its usual form of P power equals I times V. In general, the work will come from a force acting over a distance and is given by W equals the integral from point 1 to point 2 of the force F dotted with the displacement ds. If the work There are many types of work that can be done in a system. One of the more popular ones is from electrical power. Note that power is energy over time, so power is actually equal to the rate of work being done, or capital W dot. Electrical power is then given by voltage times current, or W dot equals phi times I, where I is current, and voltage has been given the symbol phi here, mainly because we already have way too many V's in this class. You may be more familiar with this equation in its usual form of P power equals I times V. In general, the work will come from a force acting over a distance, and is given by W equals the integral from point 1 to point 2 of the force F dotted with the displacement ds. If the force is constant and in the same direction as the displacement, then the work is simply equal to the force F times the displacement delta S. The force F can be any force. There are a few common forces used in this class, including gravity, springs, and shaft work. The work done to raise a body in a gravitational field is the same as the change in potential energy, or W sub g equals mgz. Similarly, the work done to compress or extend a spring is equal to W spring equals 1/2 k x2 squared minus x1 squared. For the shaft work, the force is the torque T divided by the radius of the shaft, while the displacement is the distance around the shaft, 2 pi r, times the number of turns, n. Therefore, the shaft work becomes W shaft equals 2 pi nt. Another form of work we see a lot in this class has to do with changes in pressure or volume. Either the pressure changes, in which case the work put in is this change in pressure times the volume, delta P times V. If the volume changes, then we have P times delta V. In the most general case, if both volume and pressure can change, then the work is given by the difference between the initial and final states, or W equals P2V2 minus P1V1, or final pressure times volume minus initial pressure times volume. Finally for today, a concept that is important to flowing fluids is the flow rate. This usually refers to the volumetric flow rate. That is the volume of fluid passing a certain point over a given period of time. Being a rate, the flow rate is defined as V dot, which is volume divided by time. Its official definition is the integral of the velocity across the cross-sectional area, AC. It can also be defined as V average times AC, where V average is the average velocity of the fluid across the cross-sectional area, AC. This is all not to be confused with the mass flow rate, m dot, which is the amount of mass of the fluid across a certain point in a certain amount of time. This is very similar to the volume flow rate, but also incorporates the density of the fluid, rho. Remember that volume times density gives mass. And finally, we have an energy flow rate, E dot, which is the amount of energy passing a certain point over a certain period of time. This is most easily calculated by multiplying the specific energy of the fluid, little e, by the mass flow rate, m dot. Last slide, we have the pre-lecture example for today's video. Give it a try. If you have any questions on this example or anything else in this video, please ask them in class, and see you then.